Hello class, and thank you for watching. Today's topic, rates of change in linear quadratic functions. The objective here is that you will determine the average rate of change for sequences and functions including linear, quadratic, and other function types. You will determine the change of linear, quadratic, and other function types in terms of how they're changing and how that correlates to the rate of change. So let's look at the example that we start. Let's start with linear functions and how those change. In this example, I have that f of x is equal to 1/3 x plus 4. And let's begin by graphing this. If I graph the point again, I recall again that my y-intercept is 4. So I will have a point right there. And since the slope is 1 over 3, I go up 1 over 3 again from that position there. So if I go up 1 and count 3, I'll have a point there. Go up 1, count 3, I'll have another point there. And the same thing the other way. If I go down 1 and I go back 3, 1, 2, 3, I'll have another point right there. And back down 1 and 1, 2, 3, I'll have a point there. So if I connect these points with a straight line, let me try that again. There, much better. If I connect these points with a straight line, this function f of x equals 1/3 x plus 4 will look like this. Now, we should recall from Algebra 1, in order to determine the rate of change of this thing, all I have to do is just simply count the rise over the run. If I look at the rise over the run from one point to the other point, I see that that value is always the same number. It's always the number 1 over 3, which makes sense because this is a constant rate of change. Lines have a constant rate of change. And therefore, the rate of change is never going to be different. It's always going to be the same. Now, if we look at this table right here that represents, again, these points, -6 to +2. As you see right here, these are the points that we have. -6, +2. -3, +2. We have a point at 0, 4. And then we have a point over here at 6, 0. Okay, let's look at what the rate of change is in those values. Okay, so let's make ourselves a table where we're going to split this up into intervals. And we're going to identify our rate of change within those intervals. So we're going to look from -6, and I'm going to use the table to determine what intervals I'm going to use. So I'm going to go from -6 to -3. That will be one interval. Now from -3 to 0. And finally from 0 to 6. So using the table, I'm going to calculate again. We already know that the rate of change is 1/3, right? But again, just for practical purposes, I'm going to use the table to create intervals from one x value to the next and see what the rate of change is there. So to figure out the rate of change, recall that the formula that we're going to use again is y2 minus y1 over x2 minus x1. And since I have a table here, which is just simply the change in y divided by the change in x, since I have a table here, I already have them sorted out. So instead of plugging it in with the table, it's just easier to do this, is to figure out the difference from 2 to 3. That's going to be the change in y. That's going to do y2 minus y1, and I'm going to write that information right here. So 3 minus 2. 3 minus 2 equals 1. And when I subtract going back upwards like this, that's going to do x2 minus x1. So this is my x2 minus my x1, and I'm going to write the answer right here on the side. So -3 minus -6, that's equal to a total of 3. And since we get the ratio of this is my change in y. This is my change in x. And that's what, again, the rate of change does. y2 minus y1 is simply finding the change in y. x2 minus x1 is simply finding my change in x. I can determine what the rate of change is by getting this number and dividing it by that. So we end up with a rate of change of 1 over 3. Now if I look at the next interval from negative 3 to 0, the y value here, the y2 and the y1 are 4 and 3. So 4 minus 3, that again is 1. And the x2 minus the x1 is 0, negative 3. So 0 minus negative 3 is also 3. So now to get the rate of change, is simply get the change in y and divide it by the change of x. So 1 divided by 3 again. So you see, again, this rate of change is 1 over 3. This rate of change is 1 over 3. That's all I've done, just using, again, the table. And now I'm going to find the rate of change from this point to there, which is 2 over 6, which is going to reduce to 1 over 3, as you see, like 2 over 6. And that reduces to 1 over 3. But let me again show you how to do this with the table. So right here, instead of writing the formula over and over again, with a table is really convenient to figure out the rate of change. Because all I'm doing again, let me use a different color, this one right here. My y2 is going to be 6, and now my y1 will be 4. So 6 minus 4 is 2, and my x2 is 6, minus my x1, which is 0, and 6 minus 0 is 6. So when I do 2 divided by 6, that reduces to 1 over 3. And again, the point that I'm trying to get across here is that since we have a straight line, notice that the rate of change is constant, okay? These numbers are always the same. Red, important. Our rate of change is constant because f is linear. This is why this function is constant, because the function is linear. And that's going to again be key. Every single time we have a straight line, our rate of change again is always the same. Which again is something that you should come in knowing, because this is what you studied in Algebra 1, that lines always have a constant rate of change. And again, we're just using what we've learned about how to determine the average rate of change to figure out and prove again and verify that this is going to still be true. So fill in the bottom part right here. So right here is essentially what we wrote. For linear functions, the average rate of change over any length interval, all right? So any length input value interval is constant. Which, as you saw, look, if I look at the table, my intervals were going by 3. So negative 6 to negative 3 to 0, they were all going by 3. But then from 0 to 6, it went by 6. So it doesn't matter what length interval I use. When I looked at the rate of change, dividing again the change in y over the change of 6 reduced again to the fraction 1 over 3. It still gave me the exact same value. So regardless of how long I make the length of the intervals of the x values, my rate of change is always going to be constant. And since the rate of change is constant, the graph of a linear function sorry, I lost my train of thought here. So like I was saying, since the rate of change is constant, the graph of a linear function does not have concavity. Because again, correlating from the last assignment, concavity, again, the way it curves is correlated with rate of change. If the rate of change is increasing, our ROC is becoming bigger or getting smaller. Getting bigger means it concaves up. If these numbers were getting smaller, then it's concaving downward. And because, again, as you see on the picture, it has no curvature. It's straight. So it makes sense again that the number would have to be the same because it has no curvature. So if you want to think of from that perspective, this is another way of understanding why this number is always going to be the same for straight lines, because it has no curve. Now let's look at quadratics. Well, in a quadratic, first thing you notice again is not a straight line, so the rate of change is not going to be the same. So let's figure out what the rate of change is going to look like for this thing right here. So let's look at using again these intervals of this table here. So let's make a table. We're going to write interval, rate of change, and we're going to create the intervals from -3 to -2. Okay, -2 to -1, -1 to 0, 0 to 1, 1 to 2, and 2 to 3. Now this would look like it would take a long time to figure out the average rate of change, but since we have a graph, we can use, since we have the table, we can use the table because it's pretty much set up for us, and all we have to do is figure out the change in y and divide it by the change in x. So let's start from -3 to -2. So to figure out the change in y of this portion right here, I'll do it in blue, this portion right there. Again, let me write the formula down here. Our rock average rate of change is the change in y over the change in x, which again is y2 minus y1 over x2 minus x1. So we're going to subtract the y. So 4 minus 9, that's equal to -5. -2 minus -3 is +1. So the rate of change is -5. -5 divided by 1 is that. Now let's look at the rate of change on the interval from -2 to 1. So here in this interval. So the change in y would be 1 minus 4, which is -3. And -1 minus -2, that's +1. So -3 divided by 1, that is -3. Now let's look at the next interval from -1 to 0. So this interval right there, we're going to subtract the y. So 1 minus 0, that's -1. And 0 minus -1 is +1. And the change in y over the change of x, that's -1. Now here, this has a change of +1 and +1. So our rate of change is 1. Our rate of change is 1. Here the change in the y's is 3. Here the change in our y's is 1. So this is equal to 3. And our change in for the last interval, our change in our y is 5. And the change in our x's is 1. So 5 divided by 1 is 5. Now the first thing that you notice obviously is that the rate of change again is not the same. The numbers again are different. And if we correlate again to what we learned in the previous lesson, well, we see that these numbers are getting bigger. All right, -5 to -3 to -1 to 1 to 3 and 5 are getting bigger, which again correlates perfectly to this idea because the graph concaves upwards. So it makes sense that this number again would get bigger, as explained again in the previous lesson. The one thing I want you to pay attention to now is by how much the rate of change is increasing in this equal length intervals. Notice that the intervals are all a length of 1, as you saw right here. Look, I'm changing all my x values an equal length of 1. So every equal length input value interval that I have, notice that the y values are all increasing by 2. They go up by 2. From -3 to -1, that is +2. The way I'm 2. from -1 to +1, that goes up 2. From here to here, that goes up 2. And from here to here, that goes up 2. So what we see here is that we have a change. I'm going to write this in this color here, that the rate of change changes, all right, okay, by +2. And if you look at what that looks like a straight line right here. So in other words, your rate of change again changes at a constant rate. And let me write that one there, okay? So our rate of change changes at a constant rate. So if our rate of change is not the same, obviously it's not going to be a straight line. So these numbers are not all the same number. It is not a straight line. But if our rate of change is increasing or decreasing at a constant rate, so if our rate of change is changing at a constant rate, then what does this mean? Well, what this means is that this graph again is not a linear function, but it's going to be a degree 2 function. Because after a second rate of change, looking at a second change, we see that that number is now consistent. So how does this correlate to this quadratic function? Well, that's going to be true with any quadratic function. Notice that it only took one rate of change to find a consistent value. All those numbers were the same. And when I took the rate of change the first time on the quadratic, they weren't the same. But then if I took the rate of change of that value, I then noticed that the rate of change was consistent. So if I looked at a second time, then I see that the numbers are the same. And what does that mean? It means that it correlates to this power right there. Having it done a second time, that means that we have a function that is raised to the second power. So hence we have this quadratic function. And that's the correlation in today's concept and today's lesson, is making the connection that I can identify when a function is linear or quadratic by looking at its rate of change. And again, I know I'm sounding like a broken record here, but when our rate of change again is constant the first time, it means it's linear. And when it's not, but on second time it is, then it's going to be again quadratic, like in this example here. So the average rate of change of our rate of change is always a constant value of 2. Okay, it's always increasing by the same amount of 2. So what does this mean about the average rate of change? Well, at in equal length intervals of 1, okay, the rate of change is increasing by 2. Okay, so well, what does that mean? What this means is that for quadratics, so for quadratic functions, the rate of change are given by linear functions over consecutive intervals. So what that means is that that for a quadratic, the average rate of change is not going to be a straight line. The average rate of change is going to be increasing at an interval in this situation, because it was increasing by 2, like this. It's going to be going up. This is what the average rate of change is going to look like for quadratics. And I didn't draw this on the other one. Let me go draw this graph on the lines. Okay. I'm sorry about this. We're going to have to go move this out of the way here. That for this graph right here, since the number is the same, the average rate of change for this looks like this, because it's always the same number. Okay. Well, in this situation, it's 1 over 3, so it should be a little bit higher. Right here at 1 over 3. A straight line, because we're increasing by the same value. Now, how do we use this? Well, the way we're going to use this is use this understanding in order to determine, if we're given a table of values, to classify whether the table represents a linear or a quadratic function. So for example, right here, we're going to create a table, a horizontal table. We're going to write interval and rate of change, and see that when I use the interval from one x value to the next, see if this rate of change is going to be the same number, constant, or it's going to be increasing by a constant. So let's look at this. Okay, so the formula that we used, since we have a table, y2 minus y1 would just simply be 1 minus 0 first. And this would be 2 minus 1, which is 1. 1 minus 0 is 1. So 1 divided by 1 is 1. Now here, this is 4 divided by 1. That's equal to 3. 3 divided by 2. I'm sorry, 3 minus, not divided, I mean minus. 4 minus 1 is 3. And 3 minus 2 is 1. And 3 divided by 1 is 3. 9 minus 4 is 5, and 4 minus 3 is 1. So again, to get the change in y2 minus y1 over x2 minus x1 with the table, this is the fastest way of doing it. And then 5 divided by 1, that's equal to 5. So obviously these numbers are not the same. Since these numbers are not the same, then this cannot be linear, all right? So it is not linear. Now, in order for it to be quadratic, there has to be a constant. The rate of change has to change by the same number. So we have to have a constant rate of change between these numbers right here. And we do. These numbers increase by 2. From 1 to 3, that's an increase of 2. And from 3 to 5, that's also an increase of 2. So this thing right here, this table, represents a quadratic function. And the reason is for that is because, this is my symbol for because. Again, because your average rate of change increases by a constant. Okay? Because it's changing by the same value. So let's look at the next example. Let's look at example B. Let's see. So for this example right here, again, let's make a table just like before so we could organize this. Our intervals, our average rate of change, and we're going to go from 1 to 2, 2 to 5, and 5 to 10. And let's see what the average rate of change. So 1 minus 0 is 1, 2 minus 1 is 1, so that's equal to 1. 4 minus 1, that's a total of 3. And 5 minus 2 is a total of 3 as well. 3 divided by 3, that's equal to 1. And 9 minus 4, that's equal to 5. And 10 minus 5 is also 5. And 5 divided by 5 is also equal to 1. Now, even though these are not equal length, okay, we can clearly see that these are not all the same length. This is a length of 1. From 1 to 2 is a distance of 1. From 2 to 5, that's a distance of 3. And from 5 to 10, that's a distance of 5. They're not equal length. We do see that when we get the average rate of change is that they're all constant. So this table right here represents a linear function because our average rate of change is constant. It's the same. Okay. Now, let me back up just a little bit. Now, what does this mean about number 1, letter A, about the concavity? Okay. Obviously, this is a quadratic, and we have two options here. Our quadratic can open upwards, or our quadratic can open downwards. And how will we determine that? Well, easily. Look at how the rate of change is changing. So our rate of change is increasing by a constant increasing, then that means it's concaving upwards. So this quadratic should be a quadratic that looks like that. Okay, so it concaves upwards. And let's look at the last example. So in this example right here, one to 3, 3 to 5, 5 to 7. So let's see, this is a difference of 2, this is a difference of 2, 2 over 2 is 1, this is a difference of 1, this is a difference of 2, so that's 1/2, this is a difference of 0, and this is a difference of 2, 0 divided by 2, that's equal to 0. So let's see here. So it's not linear, obviously, because it's not constant. But let's see how it's changing. Here we go from 1/2 to, from 1 to 1/2. So that is a difference of negative 1/2. We go down by 1/2. And from 1/2 to 0, that's also changing by negative 1/2. So this could possibly be a quadratic, or we'll say it's a quadratic. It's a quadratic function because our average rate of change decreases by a constant, which is negative 1/2. Now, how does that correlate to concavity? Well, it concaves downwards since we're decreasing, again, the average rate of change by the same number every single time. So let's use that idea again and select the values for the function of k, m, and p are given in the table below. And for each function, determine if the function would concave up, concave down, or neither over its domain. So we have selected values of these three different functions. So let's start off with function k. All right, function k, letter A. And let's see if it's going to concave up or down. So again, we're going to create intervals and see what the rate of change is. So we'll go from 1 to 1.1. So this right here is a difference of 3. 1 minus 4 is 3, and this is a difference of 0.1. So this is negative 30. From here to here, from 1 to negative 1, that's a difference of, you are going down 3 as well. And this is a difference of 0.1. So negative 3 divided by 0.1, that is negative 30 as well. And we're going from 1.1 to 1.2. And now we're going to finally go from 1.2 to 1.3. This is a difference of, oh no, hold on, I made a mistake. This is 2 minus 2, so negative 20. And from negative 2 to negative 1, that's a difference of minus 1. And again, this difference from 1.3 to 1.2 to 1.3, that's a difference of 0.1. So again, 1.3 minus 1.2, that's how you figure out again the difference. The way to figure out the difference from this point to this point is just subtract remember, the second one minus the first one. So that gives you 0.1, and negative 1 divided by 0.1 is negative 10. So this thing is not linear. It's going to be, again, curved. It's not going to be a straight line because, again, our rate of change is not the same. And since we're going from negative 30 to negative 20 to negative 10, that's an increase. We are increasing by 10 every single time. So since, again, we're increasing, that means that this k of x concaves up on the interval of x from 1 to 1.3. Now let's look at the next example. So for our next example, I'm just going to abbreviate interval now and rate of change here. We're going to go from 1 to 1.1, 1.1 to 1.2, and 1.2 to 1.3. So again, all of these are all changing by the same unit as before, 0.1. So no reason to do that again. We did that in a previous example. From 1 to 4, 4 minus 1, that's equal to 3. 7 minus 4, that's equal to 3. And 10 minus 4, that's equal to 3 as well. So 3 divided by 0.1, that's equal to 30. 3 divided by another 0.1, that's also equal to 30. And the final 3 divided by our 0.1, that's also equal to 30. So in this example right here, since our rate of change is the same, all right, that means that we just simply have a diagonal line, a line that goes upwards. And I know it goes upwards because, again, the y values are increasing, right? 1 to 4 to 7 to 10, again, are getting bigger, so the y values are getting bigger from this point of 1 all the way to 1.3 in that little section. So the graph is a straight line. And because it's a straight line, again, it has no curvature. So does not concave. So no concavity. Curvature, all right? No curvature. And let's check the last one. So for the last example, so for our last example here, again, these are changing by 0.1. 1 to 7 is a change of 6. This is a change of 4. And the change of 2. So from 1 to 1.1, we're changing by 60. I'm sorry, yeah, we have a rate of change of 60. 1.1 to 1.2. Let me zoom in here. We have a change of 4 divided by 0.1, that's 40. And then from 1.2 to 1.3, we have a change of 20. So obviously this does have a curvature because it's not a constant rate of change, but we're going down. These numbers are decreasing by -20. So it's a quadratic. It could possibly represent a quadratic that's concaving downwards. So there you have it. All right, so that concludes again our notes. And just to recap, we can use the rate of change not only to determine if our graph concaves up and down, but also to determine if we have a straight line or a quadratic. Okay. Now, if we didn't do an example of this, but if none of this is true, where our rate of change is not the same, like in this example B, or it's increasing or decreasing by the same amount, all right, then if none of these two things are happening, then it has to be some other type of function. Okay, doesn't mean it's not a function, it's just going to be a different type of function. But for all linear functions, the rate of change should be the same. And for all quadratic functions, again, your rate of change should be increasing or decreasing by the same amount every single time. All right, so there you have it. Again, I appreciate you watching, and like always, I hope you have a great day. Goodbye.